All right, using polyatomic anions in naming compounds. This is why you need to know the representative ATE ion. So take your ATE ion, whether it's chlorate, nitrate, carbonate, phosphate, the naming scheme is going to be the same. So here's chlorate. It's a ClO3 with a -1 charge. This is the somewhat of a Lewis structure for chlorate. You've got a minus charge on it, and we call it chlor8. Now, what happens if I reduce the number of oxygens? Notice that the charge doesn't change. The charge is still -1, but the number of oxygens has changed, and so the name is going to change. We're going to go from chlor8 to chlorite. Okay, so this will be chlorite. Now the same thing would be true if I had nitrate and I removed one oxygen. So just for instance, nitrate is NO3 with a -1 charge, and nitrite is NO2 with a -1 charge, in the same way that chlorate goes to chlorite. Okay, so this is nitrite. The only thing that's changed is the ending of the name. This is nitrate. We just went from ate to ite, and that's it. Okay? The same thing would be true for phosphate. All right, so here we go. Let's go down one more oxygen. I'm really low in oxygen here, but notice I still have just a -1 charge. Okay, so this is still a -1 charge. Even though I'm way down on oxygen, I still have the same charge. So we're going to change the name. We're going to keep the ITE ending, but we're going to add a prefix, hypo. If you're familiar with hypodermic syringes, hypo means underneath the skin. I interpret that as really low in oxygen. Okay, my oxygen content in my polyatomic anion is really low, so I call it hypo, meaning I'm really low in the stuff. But I keep the ITE ending. So I've gone from chlorate to chlorite to hypochlorite. If I were to have something like this, I would call this hyponitrite. Okay? So you've got ate, ite, and hypoite. That's how you think about this. Okay? All right. Let's take a look at going the other way. Let's stick with chlorate, and this time instead of removing an oxygen, we're going to add an oxygen. So one way of saying you have like too much energy is you're really hyper. So I'm thinking, well, we've got a lot of oxygen here, and so we're just going to lose the high, very sad, and keep the per, and keep the 8. So this is perchlorate. Okay? So let's do something with phosphate. So here is PO4 with a 3 minus charge. That's phosphate. So if I had something like this, PO5 with a 3 minus charge, I would call this perphosphate. Okay, so the naming scheme for the oxoanions is really the same, but you have to know the ATE ion. So I'm going to take us back very quickly and take a look at your polyatomic ions. That's why you need to know that chlorate is ClO3, nitrate is NO3, and it's got a -1 charge. Carbonate is CO3 with a 2- charge. Okay, and then chromate, CrO4 with a 2- charge. Sulfate. So you tell me, if I had, instead of sulfate, I had SO3 with a 2- charge, what would that be? Well, it's not sulfate because SO4 with a 2- charge is sulfate. This would be sulfite. The ending would change to ITE. And that's the way we do that. If I gave you SO5 with a 2- charge, this would be sulfate. Okay, just because I've added an oxygen to sulfate, so we add the prefix per and we keep that ATE ending. The charge does not change. So let's name this ionic compound. You know it's ionic because it's got a metal and it's got a polyatomic anion. So is the metal of known charge? The answer is yes. It's a group 1 alkali metal. It's potassium. I guess that wasn't too big a mystery since I've got all of these as just potassium. We don't need to name the charge because it's a known charge. And look at this guy right here. Well, let's start out with the ATE version. This is chlorate. We went to chlorite, but we went all the way down to ClO-, which is hypochlorite. Okay, so this is potassium hypochlorite. A little bit of practice. What if I had given you something like this, KClO4? What would that have been? Well, it would still be potassium, but it would be perchlorate. So this would have been potassium perchlorate. Okay? The per, because I've got an extra oxygen above the ClO3 chlorate polyatomic anion. Okay? All right. Practice. How about this? Ionic or molecular? Well, this is a metal, and it's got a polyatomic anion. So this is an ionic compound. Okay? No prefixes, and is the metal of known charge. That is it group 1, group 2, is it aluminum, is it zinc, or is it silver? And the answer is no. So here's our naming scheme. We need to name the metal, we need to put the charge in Roman numerals in parentheses, and then since this is a polyatomic anion, we need to name the polyatomic anion. Okay? Anion. All right, so here we go. Now, how do I figure out what the charge is? Well, I look at this guy right here. This is SO4. Let me think back to my list of polyatomic anions. And I remember, well, this is sulfate, and it had a 2- charge. Now, all compounds are neutral in charge. That's the nature of compounds. So that means the number of positive charges has to equal the number of negative charges. Since I have one -2 charge over here, so that's -2, this has to be +2. So this would be iron. I hope you recognize that Fe is iron. In parentheses, Roman numeral 2, and then sulfate. Iron 2 sulfate is the name of this compound. What if instead of iron 2 sulfate, it had been FeSO3? Then it would have been iron 2, because the charge doesn't change on this polyatomic anion, it would have been sulfite. And do not capitalize that second letter, the second letter here. Okay, don't capitalize sulfite. You can capitalize the iron if you want, but don't capitalize the sulfite. Okay, writing ionic formulas. The chemical formula for an ionic compound is always written as an empirical formula. Let me remind you of why. Remember, ionic compounds are crystals, and crystals of ions are just made up of ratios of cation to anion. Cation, little blue guys here, to anion, and so on. There are no, I can't tell you exactly how many sodium cations and how many chloride anions are represented in this crystal. I can tell you this: the ratio is 1 to 1. Okay, that I can tell you, and that is all I can tell you about an ionic compound, is the ratio of ions to each other. And remember, empirical formulas are just the simplest ratio of ions that are in the compound. And so, when we're writing an ionic compound, we always write it as that simplest whole number ratio, like sodium chloride. So here is sodium chloride. Now all we have to do is balance the charge, because remember, all compounds are neutral. And so if I want to balance the charge on this compound, all I have to do is do my little crisscross here. Now, I'm not moving the negative charge over here. I'm not moving the positive charge over here. I'm telling myself, how many of these negatively charged chloride ions do I need to balance the positive charge on the sodium cation? That's what I'm doing. There is an implied 1 here and an implied 1 here. And we never write the 1s as subscripts, only if it's greater than 1. So the formula for sodium chloride is simply NaCl, understanding that there's a 1 here and a 1 here. This is not a molecule. Remember, it's a crystal. It's an extended array, a ratio of 1 to 1 in this particular case. All right? All right, let's take a look at the next one. Now remember, all we're going to do here is we're going to balance charge. The iron in this case has a +3 charge. The bromide ion, which is a halogen, it's in group 7, has a -1 charge. If I'm going to make an ionic compound out of these two ions, I need to have just as many -1 charges as I do +3 charges. So my ratio is going to be 3 bromide ions to 1 iron 3 plus cation. So you can just imagine that up here I could say, yeah, that's 3 plus, this is a -1, but I'm multiplying it times 3 to get a total negative charge of -3. The -3 and the +3, they neutralize each other so that this is a neutrally charged compound. No charge. It's neutral. So the number of negative charges have to balance the number of positive charges. All right? Let's see if you can figure this one out. And by the way, the name of this compound would be iron 3 bromide. How about this guy over here? This is going to be magnesium nitride. We're going to do the same trick. We are going to just do our little crisscross here. Now, this is telling me I need 3 plus 2 magnesiums to balance the 2 minus 3 nitrogens. So that's going to give us this formula. Why is this? Think about it this way. Each one of the magnesiums is 2 plus. Each one of the nitrogens is 3 plus. If I split these up just to check out charges, I have 2 times a minus 3, which is a total of negative 6. I have a 3 times a plus 2, which is a total of plus 6. The plus 6 plus the minus 6 equals 0 charge, and all compounds are neutral. So whatever the charges are on the individual ions are, I have to have enough of each to neutralize all charges to get to 0. And remember, all ionic compounds have to be written as empirical formulas. That is, I can't reduce these formula any lower. Let me give you an example. So I want to make a compound out of lead that has a plus 4 charge and oxygen that has a 2 minus charge. And I'm going to do that same little crisscross trick. So here it is. I crisscross. Now, what is that telling me I should get? It says, well, I'm going to have 2 of my plus 4 leads. So that would be Pb subscript 2. What's my subscript for oxygen? Oh, I need 4 of my minus 2 oxygens. So that's going to be 4. And that seems to make sense because that's a minus 2. That's a plus 4. 4 times a minus 2, that equals negative 8. 2 times a plus 4, that's a plus 8. These are 8s. Plus 8 plus a minus 8 equals 0. What's wrong with that? Well, this is not written as an empirical formula. And I want to remind you one more time. Ionic compounds are written as the simplest ratio of the elements that are in the compound, all right? So they have to be the simplest ratio. So I'm going to divide both of these by 2. This is going to give me a 1. That's going to give me a 2. This is lead 4 oxide. Okay, this is lead 4 oxide. Now, I can tell it's lead. If I were just given the formula, I could tell that it's lead 4 because I know from the periodic table that the oxygen is minus 2. 2 times a minus 2, that's minus 4. All compounds are neutral, so that's got to be a plus 4 here. So this would be lead. I'm out of room. So here's my compound, PbO2. We figured out that's plus 4, that's a minus 2. This would be lead, parentheses, Roman numeral 4. It's binary, oxide. Okay, I think that is, well, let's do one more little slide and then we'll call it a day. All right, this is a long video. Which of the following molecules contains 4 ions? Well, we'll make short work of this. This is an ionic compound, and the subscript here is 1. The subscript here is 2, so that's just going to be 3 ions. What you have here is 1 magnesium 2 plus cation, and you have 2 discrete bromide anions. This is not, here's one thing that students do often. With ionic compounds, this does not mean that's a diatomic molecule. That's actually two discrete bromide ions. This, if we split it up, we've got a 1 here, we've got a 1 here. If we split that up, calcium is an alkaline earth metal, and in ionic compounds, those are all +2 ions. And then we have one polyatomic carbonate ion with a -2. So that's 1 ion plus 1 ion, and that equals 2 total ions. This is aluminum nitrate. We're going to split this up. Now, whenever I have a set of parentheses like I have here, everything inside the parentheses is multiplied by the subscript outside the parentheses. So that's going to give me 1 aluminum ion, and if you remember from the periodic table, aluminum is that +3 ion. It's always +3, it's never different. And then you're going to have 3 polyatomic anions. That's 1 plus 3, or 4 ions. And then finally, we've got this. This is your 1 polyatomic cation. Remember, we've got parentheses here, and there's a subscript 2. That means I have 2 of those. So I have 2 NH4 ammonium cations, and I have 1 chromate 2- anion. Okay, I got 2 +1s and 1 -2 ions, so that's 2 ions. And then here I've got a molecular compound. This is actually acetylene, kind of looks like this. And you got a hydrogen out here. That's a molecule, and that is a molecular compound. So it has 0 ions. Remember, ionic compounds have ions. Molecular compounds are made up of atoms. And that, ladies and gentlemen, I think is enough for today.